something there. So, all right, I do want to talk about last week's project before we move on to this week's. So we had the needle drop. I want to talk about it and kind of show. I found this experiment, and so I assigned it to you guys. And your numbers kind of bounced around a little bit. Your first calculation after your first drop was like a 2.8, and then it went to a 3.3, and then anyway 2.9, 4.7, 4.2, 2.8, 3.7. Got a bunch around between 2 and 4. A little bit like a random, and it may be it's because of the size of the sample. I found this simulation. Let me put this up on the screen. I found an online simulator for this experiment. So here's this online simulator, and like you could drop like 1 if you wanted to. Okay, so our calculation is 0 because it didn't land on the line, or you can drop 10 at a time, drop 100 at a time. And it's that bottom number down there is calculating. So right now it's at 3. So if I drop 1,000, now it's at 3.22. Let's drop 100,000 at a time and see that very bottom number on the screen. So what that ends up. So we drop, now it's 3.156. Let's drop another 100,000. So that'll put us over 200,000 dropped. Now we're at 3.14319. 3.1455. The more we drop, the more it's kind of staying in the same area. Look at that, 3.145, 3.146, 3.145, 6. Okay, we've dropped 1 million now, and it's at 3.14521029. Interesting. You'd think. I mean, you were getting between 2 and 4, kind of in that range, but only dropped 100, right? So now we've dropped 1 million, and it's gotten a lot tighter to where it's always around 3.14 something. So let's drop a few hundred more thousand. Yeah, it's not really moving. The overall number is very consistent. So it's coming down a little bit, 3.142, 3. Yeah. So we're at 2 million now, 3.1429. So what does that remind you of? 3.14. Recognize that number in math? 3.142. Number's kind of coming down a little bit. Now it's at 3.1419. Back up to 2.3, back up to 2.9. Getting a bunch of them on the line. The reason we're doing Wednesday instead of Friday is I do want to give a little bit of time so that someone. So we've dropped 3.5 million in this simulation, and we're at 3.1426. Supposedly, this experiment, the more you drop, the closer that actually gets to pi. Because pi is 3.14159, right? And we're pretty close to that, 3.1426. At 3.5 million drops. So this is something they say simulates, Buffon's needle simulates the value of pi when you take 2 times the number dropped divided by the number that fall on the line. Interesting how pi shows up in this experiment, because we expect pi in something when we're talking about circles, right? Because that has to do with circumference and all of that diameter, you use pi. This has nothing to do with circles. This is all straight lines. And yet pi shows up. Pi shows up in these calculations. You start over, drop 100,000, 3.1423 right there in the first drop, first 100,000. Crazy. But this is something that has been around for quite a while, actually. This Buffon's experiment. First dated in 1777. So 250 years ago. It's one of the oldest problems in the field of geometrical probability. I had one student whose calculations got really close to pi, and then by the time they dropped 100, it's random for a while, but the more you drop, the less random it'll be. Excuse me. So just something I thought you might be interested in. Math is interesting how it's all around us. So with that, let's look at what we're going to do this week. So I want to put these rectangles up, and I just want to take a survey of the two of you, and you can put this in the chat if you like. But of these rectangles, which one is most pleasing to the eye? It's interesting that we like some shapes better than like other shapes. These are all rectangles, but is there any rectangle that just feels more like the right rectangle than another one? G or H? Okay. Aiden says G or H. What do you think, Marion?
Yeah. Well, maybe even I.
Maybe even I. You like the really long rectangle.
I don't know.
Well, I mean, there's not a wrong answer. It's whichever one just.
They're all rectangles.
They're all rectangles, but is any one more pleasing to the eye than others?
Yeah, I'd probably agree with like Aiden, like G or H.
Okay. All right. Well, it's interesting. I'll tell you, there was an experiment done like this back in the 1860s, 160 years ago, where a psychologist named Gustav Fechner had these 9 triangles, and he had a bunch of people look at it and say, all right, which one of these would be your favorite rectangle? And most of theirs revolved around either C, D, or F. And at the end, the winner was actually D. D was the one that most people found, okay, that just seems to be the right shape of a rectangle. D. So we're going to get into really what that means here. Let me advance this. We're going to talk about the Fibonacci sequence first. Have you ever heard of Fibonacci, the Fibonacci sequence? He was an Italian mathematician, lived from 1170 to 1240. It wasn't his actual name. His name was Leonardo of Pisa. He was there around the time they were actually building the Leaning Tower of Pisa. It wasn't leaning when they were building it, but so he was young when they were building that. But he submitted this to mathematical papers called the Fibonacci sequence. Fibonacci was the name he used. He said, here's this sequence I've discovered in math. And he used the pen name Fibonacci, which really meant a fool. People thought it was foolish, and Fibonacci was what they would call it, because that's just crazy. It doesn't mean anything. But his sequence is 1, 1, 2, 3, 5, 8, 13. And we'll show how it gets there. This is how he come up with his sequence. He said, if you start with 1, well, actually you can start with 0 and 1, and add them together. The next number would be whatever is when you add those two together. So when you start at the beginning and have 1, 1, when you add those together, you get 2. So then you take those two, 1 and 2, and add them together, and you get 3. 2 and 3 equal 5. 3 and 5 equal 8. So to get the next number, you just add the last two numbers together. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 1 is 34. And you can go on forever with that. 89 plus 144 is 233. 144 and 233 is 377. So it's just adding the last two numbers. And it became known as the Fibonacci sequence. And for a while, people were like, okay, that's just craziness. It's not useful. It doesn't have anything to do with anything. But does it? Because what we're discovering is you can arrange this in interesting ways. If you look at a square, okay, this is a square that's a 1 by 1, and you put another 1 by 1 to it, and then put a 2 by 2, and then a 3 by 3, and then a 5 by 5, and then put an 8 by 8, and just use those Fibonacci numbers, and then a 13 by 13. Then the next one is the 21 by 21 and the 34 by 34. And you just keep adding those on there. It kind of makes an interesting design. It makes this interesting design because if you start at the beginning, you can put this curve, this spiral that connects the diagonals of all of those squares derived from the Fibonacci sequence. And it makes this interesting shape that it turns out appears a lot in nature. In reality, we see this same spiral And they call this the golden spiral because it comes from this Fibonacci sequence and it can be found over and over again. Again, that sequence was divided by a 5x5, so it's 25 square units, but it's using the Fibonacci 5x5, the 8x8. But, oh, there it is right there. So, it's a 1x1, a 1x1, 2x2, 3x3. It uses those Fibonacci numbers. So with that, you end up with this little sequence. And there's the squares, when you square each of those. 1, 1, 4, 9, 25, all that kind of stuff. But what they discovered is this Fibonacci sequence, there's a definite pattern every time. When you go through the numbers, the 1, the 3, all of those, when you go through these, there it is, 34, 55, 89, 144, 233, every number, if you divide the larger number by the number right in front of it, it's 1.618 every time. 233 divided by 144, 1.618. 377 divided by 233, 1.618. This sequence starts to make sense in that there's a very consistent pattern. If you divide the other way, 0.89 divided by 144, it's 0.618. 55 divided by 89, 0.618. So depending on which way you divide it, but there's always this consistent number that appears in the Fibonacci sequence. And so it really got a lot of people's attention the more they started studying it and the more they looked at it. And what we found out is using that, this rectangle that was chosen by the most people in that experiment that they did back in 1860, that's the dimensions. If this is a 1, this is 1.618 long, which kind of goes with the Fibonacci sequence. The next number is 1.618 larger. And so this has come to be known as the golden rectangle. And by the way, that 1.618 is a number called phi. They gave it a name like pi and E and I. This is phi. It's the Greek letter phi, P-H-I. The golden rectangle. So what they started noticing is that the golden rectangle is very pleasing to the eye, or at least they think so. There's been other people dispute it and say, no, we've just trained ourselves. We've trained ourselves to say that's appealing. Fibonacci was a fool. He didn't know what he's talking about. Others are like, Fibonacci's onto something because he's found the mathematical equation for what's most pleasing to people to see. But when they see this, when you see that golden spiral and you see the golden rectangle, you can find it in nature. See, there's that spiral. When you cut this shell in half and look at the inside of a seashell, you'll find this same spiral throughout that. One little example from nature. You'll also see it over here. It is in each wing of this butterfly. Even your ear can fit that spiral in the shape of how it works. They can apply that and find a lot of places in nature that this shows up, and it's like it's really wild. When you see on the weather, even look at that. Look at the cloud pattern from a hurricane. You can take the same diagram and lay it over it, and that really ties in nicely. Galaxies seem to have that same spiral that the Fibonacci number exposed. It's pretty cool. And so that golden rectangle, I'll show you something really fascinating because they've taken this and really gone deep with it now and gotten into some things. Oh, let me show you one more picture before we do. No, I'll go do this first. So what I have here is a square. It doesn't look like a square the way my camera's showing it, but it is. That's really weird because when I measure it, this is 12 centimeters by 12 centimeters. So it is a square, even if it looks distorted on the screen. It looks like a rectangle, but it's not. It is 12 by 12. I measured it out very carefully this morning and made this square. So if I take the square, and this is the middle point. This is the middle point. I've marked, 6 6 centimeters. That's the middle point. And I go from this top corner to the middle of the square. And I make that line right there. If I take this line, and let me see exactly how long this line is. This is 13.4. 13.4. If I could physically grab this line and bring it down, right? If I just bring it down flat, it would look like this. Let me make the line down here. I said it was 13.4. So I'm going to extend this out. 13.4, which means I'm also going to extend this one out. Well, I need the whole line. I didn't mark the midpoint up top. So let me see. The whole line is now 19.4. So let me make this 19.4 up here. 19.4. Okay. And then I connect these points right here. This is the golden rectangle. This is the golden rectangle. If we said this side was 2, and this is 1, and this is 1, because I cut it in half. This is 2, right? Because this is a square, so all these are 2. We can figure out how long this is, because this is now a right triangle, right? That's a right triangle. So with a right triangle, 1 squared plus 2 squared equals the hypotenuse. So 1 squared is 1, 2 squared is 4. So this is the square root of 5. That's how long that is, which means this from here to here is the square root of 5, because I just took this and I brought it down to make this rectangle. So this side is now 1 plus the square root of 5. All right, 1 plus the square root of 5. So if I want to check out the ratio, and I divide 1 plus the square root of 5 divided by 2, this side compared to this side, what is the ratio of those two sides? Let's bring up our calculator. Okay, so 1 plus the square root of 5, that's 3.23, and I divide that by 2. There's that 1.618. That's the ratio of the golden rectangle. This is a 1.618 ratio derived from the Fibonacci sequence. Now, here's what's really, really interesting, and why they call this the golden rectangle. If we turn this sideways, this rectangle right here is also a 1.618 ratio. If we made this 1, this would be 1.618. Now we can figure out what this length is. This is the square root of 5 minus 1, and that would be the short side, but this would be 1.618 of that. Well, actually, in this case, we know how long this side is. This side is 2 because it's the same as this. And so if we take 2, take our calculator back up there. We take 2 times the 0.618, which is the other side of that. That means this is 1.236. So when we divide 2 divided by 1.236, we get that 1.618 again. There's 1.236. And we can confirm that by right here. We know that this length would be the square root of 5 minus 1. So let's look at the square root of 5. Square root of 5 minus 1. 1.236. That's exactly what we said it was, 1.236. So the golden rectangle is this ratio, 1.68 to 1, whatever the lengths are. And if you take a square out of it, it leaves another golden rectangle that has the same ratio. And if we were to take a square out of this, and I'd have to measure 1.236. So this is, looks like 7.3 So if I put that about the same thing right here. And we take a square out of it. That's a square. This is now a golden rectangle. We'll have the ratio of 1 to 1.618. And you can do the same thing. You can keep going, and you end up with that same spiral we saw with the Fibonacci numbers. We'll see that same spiral, starting with the big rectangle, and you cut out a square, and you end up with a smaller one, a smaller one, a smaller one. Really interesting the way that Fibonacci works in life, and finding this sequence appears in spirals, and even you see those same rectangles in architecture. This was, Pantheon, this stuff from Greece, millennia ago. And if you look at the total height and the total length and all of that, it fits that same pleasing, supposedly golden rectangle shape. And they can break down inside of that, the other rectangles go inside of it. So that's what I wanted to show you today. We want to talk about the Fibonacci number and how it relates to nature and architecture and life, and how you find these repeating patterns throughout all kinds of things. So here's your project for this week. You'll need a tape measure or a ruler, but I want you to take pictures of 3 things you can find around your house or your community or in nature, wherever, that represent a golden rectangle or a golden spiral. Could be in nature, architecture, logos, art, etc. And if you find golden rectangles, submit the pictures along with the measurements that show that it's about 1.618. It may not be exactly, it may be really close, because when we measure, we're not going to have necessarily precise measurements. If you find pictures of golden spirals, there's no measurements that you need with that. No measurements you need. I do want to show you one thing right off. One thing I noticed right away. So here's a credit card. Mr. Brock has a Mickey Mouse credit card. I'm gonna measure the centimeters. It looks like it is 8.5. Or we can say 85 millimeters. All right, 85 millimeters. And the height of it looks like 53 millimeters. 85 to 53. So let's see. 85 divided by 53. 1.60. 4. Pretty close. Pretty close to the most pleasing rectangle, according to a large survey of people. Pretty close to that golden rectangle. I don't know that that's a coincidence that they would make a credit card be the same size of what scientifically they say is the most pleasing shape to the eye. Marketing does a lot of things.
Probably did that on purpose.
I'll bet they did that on purpose. Oh, that's just kind of appealing. I like the look of that, So interesting. So I want you to just go see what you find this week. See what you may find. Art that's in it. The Mona Lisa apparently has a lot of this shape in there. So you might find art hanging in your house that has those dimensions that are that pleasing rectangle. You might find logos on products. I don't know what you're going to find. But see if you can find 3 things, take pictures of them. And if they are rectangular, give me the ratio, measure that and divide it and see if it's a 1.618. So have some fun with that. But I just want to kind of show you how all of this math stuff that they study really has a lot more meaning than we think it does, because it exists, and it's nature does these numbers. And it's like, we don't create these Fibonacci sequences, we discover them because it's already been out there in nature. All these things exist, and we're just actually putting the pieces together and going, oh, wow, that's pretty cool. So, well, I just wanted to show you some more of the cool stuff from mathematics, other than just working with algebraic equations. Some more of the cool stuff that people and math scientists, mathematicians get excited about. So that way you could kind of see some of the neat stuff that you may see stuff like that in college too. A lot of professors get excited about these type of things. So, all right. Well, I'll let you guys go. Have a wonderful week. If you need any help or anything, this is an A day, so we'll have class Wednesday and Friday if you need it. But otherwise, we'll see you next week.